Hello, folks. I hope y'all are doing okay. Today, we're going to be talking about the focus of a parabola. This is lesson 3.3 in our textbook. So our learning objectives for today, we want to be able to explore about the focus and this other thing called the directrix of a parabola. We want to be able to write equations for parabolas. And of course, as always, we want to be able to apply our mathematics into real world situations and real world knowledge to solve real world problems. So here's a diagram of a parabola, and you see some various parts drawn here. Now, none of these things necessarily represent the X or Y axis. Okay, so if I wanted to take this diagram that you see here on the page and then superimpose it on a y-axis or an x-axis, on a coordinate plane, we could do that. But these parts that you see in front of you in blue and in red represent various parts, and so we're going to talk about them today. You probably want to go ahead and draw this diagram into your notes and label things as we talk about them. So first we have the axis of symmetry. Y'all are familiar with the axis of symmetry. We talked about that in the previous lesson. This point right here, which is a new term for us, this one right here, this little dot, this point, that ordered pair, that is called the focus. And the focus always lies on the interior part of the curve of the parabola, and it always lies on the axis of symmetry. So it's going to be inside the curve of the parabola on what we would consider the interior portion of the parabola, and it will lie on the axis of symmetry. Those are two characteristics that are always true about the focus point. By the way, the plural of focus, because focus in this case means one point. If we're talking about multiple parabolas, each parabola will have their own focus, and that would be foci, F-O-C-I. So just a little FYI there in your knowledge base. The singular is focus, the plural is foci. So we have the focus here, and then we have this line here in blue, which is called the directrix. So one of the key characteristics to knowing about the directrix is to know that it will always be perpendicular to the axis of symmetry. And of course, you remember from geometry that perpendicular means that two lines form a 90-degree angle. So the axis of symmetry and the directrix are perpendicular, and you see the right angle symbol right there to indicate that. So halfway between the directrix and the focus on the axis of symmetry, halfway in between is where the vertex is located. So the vertex is always located on the axis of symmetry. We already knew that from the previous lesson, but now you know that its location is always going to be halfway between the focus point and the intersection point of the directrix along the axis of symmetry. And you'll notice the little line right here and the little line segment right here, these two little hash marks or dash marks. Of course, you remember again from your geometry days that those indicate congruent line segments. So this segment is the same length as this segment. Why? Because this cuts this segment in half. It's halfway between, it is the midpoint. We could say it is a bisecting point of the line segment that runs from the focus down here to the intersection point of the directrix and the axis of symmetry. So you see I've highlighted those there. When you pick a point somewhere along the parabola, in fact, any point along the parabola, So I picked a point right here, but you could do this with any point, anywhere along the parabola, anywhere here, anywhere down here. And you measure from that point to the focus, and then you measure down to the directrix. Now, because the directrix is a line, you could measure at a lot of different angles towards the directrix, but we always measure at a perpendicular because that will be the shortest distance to the directrix. And you'll remember from geometry, we always want the shortest distance here. So we measure that at a right angle when we draw that line from the selected point that's on the parabola somewhere to the directrix. So this line segment and this line segment have the same measure. The line segments are congruent. And so you see, once again, we have hash marks indicating congruency of line segments there. Here I'm doing the same thing again. I'm picking another point here on the parabola, and I'm measuring from this point to the focus, and then I'm measuring from this point to the directrix. And this segment and this segment are going to be congruent. They're going to be the same distance, as of course is the vertex. It is the same distance to the focus and to the directrix. And it would be true for any other point that you pick along the parabola for as far as the parabola continues. Any point along this parabola, if you measure from a point, let's say right here, you measure if you measure to the focus point, and then you measure straight down, I curved there a little bit because I'm not able to do that real straight. But if you go straight down perpendicularly to the directrix, those segments would be congruent, would be the equal length as well. So that's one of the definitions of what a parabola is. That's one of the ways we define what a parabola is based on all of these points that make up the parabola are all points that are equidistant to the focus and to the directrix. If you pick a point up here anywhere, something on the interior, or if you picked a point out here somewhere, anywhere on the exterior, it would be a different distance from like this point over here to the focus, and then that same point down to the directrix. So all the points that are not equidistant are not on the parabola. All the points that are equidistant are on the parabola. Okay? So we see in our textbook, one of our core concepts here is talking about the equations of a parabola. Now we've talked about, quadratic equations, and here we're just talking about, we're defining this as the shape, the parabola itself. And you see an equation that looks very much like what we've already learned about vertex form. Y equals A times x minus h squared plus k. But in place of A, we have replaced it with this 1 over 4p, okay? So the question is, obviously the A has been replaced by 1 over 4p, so those two values must be equal. The question is, what is p? Well, I'm going to go back to the previous slide, and I'm going to tell you what p is. P is this distance between the vertex and the directrix. This is P. Also, the distance from the vertex to the focus. This is also a value of P. So this is P, and this is defined as P because these two values are congruent. They are equal. So they're the same distance, so this would be P and this would be P. So keep in mind that the distance between the directrix up here to the focus, that would be P plus P or 2P, okay? So that will come up sometimes. Sometimes you're going to get this distance. You'll be able to figure out this distance. Sometimes you'll be given this distance or be able to calculate this distance. Sometimes they'll tell you the distance from here, the directrix, up to here in the focus. And it's our job to know, oh, that's twice as much. It's twice P. So to get the actual value just for P, I'll need to cut it in half. I'll need to divide by 2. Okay, so back to our core concept. Now that we know where the value of P comes from, we recognize that, hey, if I know this distance, or if I know this distance, so the distance between the vertex and the focus, or the distance between the vertex and the directrix, if I know how far it is between these two, I will know the value of P. And I can substitute that number in, and then I use this calculation 1/4P would be equal to A. And then I have my A value for the equation. So that's something else you want to make sure you jot down in your notes, that A is equal to 1/4P. Very important. A is equal to this right here, 1/4P. So jot that down in your notes so you will have that. One other thing I want to point out to you, you notice, of course, here we have parabolas opening up. Here we have parabolas opening down. Okay, well, you know that a parabola opens up, that is going to have a positive A value. But we know that parabolas that open down, they have been reflected across the x-axis. And in order to do that, that A value has to be negative. There has to be a negative sign there to make that happen. So one of the things we want to remember about this is that when we're measuring this distance, technically, if the parabola is opening up, we measure from the directrix to the vertex, and it's going to be a positive number. We're moving up the y-axis, or counting upwards. Or if we're moving from the vertex to the focus, we're moving up. So that's a positive measurement. If, however, the parabola is opening down, then as you go from the directrix, the directrix to the vertex, you move down, that would be a negative measure. Or from the vertex to the focus, you're moving down, that would be a negative measure, so my P value would be negative. And when, of course, if I put in a negative P value into the formula or the calculation 1/4P, and P is negative, then my 1/4P value is going to end up being a negative number, which would make perfect sense, right? Because the parabola opens down and we want A to be negative. So, sometimes we get just focused on counting those distances or figuring out those distances. Just keep in mind, oh yeah, that distance, if the parabola opens down, that distance is going to be negative because I'm starting from the directrix to the vertex, or from the vertex to the focus. I'm counting down, I'm moving down the y-axis. That would be a negative number, but if I'm going up, that will be a positive number. So you'll notice that the focus here has a formula that they give us, H comma, and not just H comma K, but K plus P, because H comma K is the vertex. We're going to move up P in number of units on the y-axis. So the y-coordinate of the focus is at K plus P. So it's really, when you have it drawn, folks, it's a lot of common sense, because you realize, oh, I know what my focus or my vertex is, and I'm going up 2 units, so I'm going to add 2 to the y-coordinate of the vertex, and I know now where the focus is located. You'll notice that for the directrix, since the directrix is a line, you know that lines are represented by equations. Okay, so just remember, points are represented by ordered pairs, but lines are represented by equations. Horizontal lines, that's a constant, and it's an equation in the constant family. When we learned about parent functions, that's a constant function. Those are always y equals and then a number. And so, in this case, we're wanting to know, where is that y, where is that line crossing the y-axis, what is that value? And so the equation for the directrix is at y equals K minus P, because K, again, is up here, the y-coordinate of the vertex. We go down P units, and that's where we are in relationship to the y-axis, for that y equals that number for that horizontal line. So that number is going to be calculated by doing k minus p, okay? So just keep those things in mind as you're doing your calculations. Now, these are, these parabolas are the parabolas that we've been seeing for quadratic functions, but it is possible for parabolas to open side to side. And that's the second part that you see here. Now, something important for you to recognize here is that these are not functions. So when this happens, you're not looking at a function because these fail the vertical line test. And if you need more information about that, ask us about that. That's an Algebra 1 concept. But these are not functions. But because they're parabolas and we're studying parabolas right now, we go ahead and include these in our discussions, even though these technically are not functions. The equations for them are not functions, but they're still equations, they're still parabolas. They still have a value squared. But you'll notice that in these equations, the x and the y have switched places. These are because the parabola is open to the side. You'll also notice that the h and the k have switched places. So, the h is still measuring x and the k is still measuring on the y-axis. It's just that within their position in the equation, things have changed. Equations that open to the right, positive p. Equations that open to the left, negative p values. All right, so we've talked about p. Let's look at one example. Find the vertex, the value of p, the axis of symmetry, the focus, and the directrix for this equation. So as I look at this equation, it's a y equals, not an x equals, and I see the x is squared. So I know, okay, this is a parabola that we're used to seeing that either opens up or down. I know that it's going to open up because I have a value that is positive for a, and I know that my h is 2, and I know that my k is negative 3, right? So there's a lot of things I know here. So I know the vertex is at 2, negative 3. I know that 1 over 4p is equal to a, and I know that in this equation, a is 1/8. So, using a little cross multiplication, 1 times 8 is 8, 4p times 1 is 4p, so 4p is equal to 8. Divide both sides by 4, p is 2. So now I know my value of p is 2. Well, if I know that p is 2, I know that from the vertex, I need to go up 2 units to find the point of the focus. And from the vertex, I need to go down 2 units to find the line that is the directrix, that horizontal line. So my axis of symmetry is at x equals h, which is, of course, x equals 2. My focus, I'm going to go up 2 units. So my vertex was at 2, negative 3. So I go up 2 units on the y-axis, and that takes me to 2, negative 1. And then finally, my directrix, I'm going to go down 2 from negative 3, and that would, of course, take me down to negative 5. And so my directrix is here at y equals negative 5. Okay? All right, folks. I hope you have a great day today, and I hope you enjoy working with the focus of a parabola. Have a great day. Bye-bye.